This episode is brought to you by Cisco Educational Premium. Did you know that Lippmann-Schwinger equation is consistent with Schrödinger equation? The Lippmann-Schwinger equation is one of the most used equations to describe particle collisions, or more precisely, scattering in quantum mechanics. It may be used in scattering of molecules, atoms, neutrons, photons, or any other particles, and is important mainly in atomic, molecular, and optical physics, nuclear physics, and particle physics, but also for seismic scattering problems in geophysics. It relates the scattering wave function with the interaction that produces the scattering potential, and therefore allows calculation of the relevant experimental parameters, scattering amplitude and cross sections. The most fundamental equation to describe any quantum phenomenon, including scattering, is the Schrödinger equation. In physical problems, this differential equation must be solved with the input of an additional set of initial or boundary conditions for the specific physical system studied. The Lippmann-Schwinger equation is equivalent to the Schrödinger equation plus the typical boundary conditions for scattering problems. In order to embed the boundary conditions, the Lippmann-Schwinger equation must be written as an integral equation. For scattering problems, the Lippmann-Schwinger equation is often more convenient than the original Schrödinger equation. The Lippmann-Schwinger equation is useful in a very lineup of situations involving two-body scattering. For three or more colliding bodies, it does not work well because of the mathematical limitations. For diff equations may be used instead. However, there are approximations that can reduce a many-body problem to a two-body problems to a set of two-body problems in a variety of cases. For example, in a collision between electrons and molecules, there may be tens or hundreds of particles involved, but the phenomenon may be reduced to a two-body problem by describing all the molecule constituent particle potential together with the pseudo-potential. In these cases, the Lippmann-Schwinger equations may be used. Of course, the main motivation of these approaches are also the possibility of doing the calculation with much lower computational efforts. From the mathematical point of view, the Lippmann-Schwinger equation in coordinate representation is an integral equation of Fredholm type. It can be solved by discretization. Since this is equivalent to the differential time-independent Schrödinger equation with appropriate boundary conditions, it can also be solved by numerical methods for differential equations. In the case of the spherically symmetric potential V, it is usually solved by partial wave analysis. For high energies or weak potential, it can be solved perturbatively by means of bond series. The method convenient also in the case of many body physics, like in description of atomic, nuclear, or molecular collisions, is the method of the R matrix or Wigner and Eisenberg. Another class of methods is based on separable separable expansion of the potential of Green operator, like the method of continued fractions of Harak and Sasakawa. Very important class of methods is based on variational principles. For example, the Schwinger-Langossos method combining the variational principle of Schwinger with Langossos algorithm. In the S matrix formulation of particle physics, which was pioneered by John Agbiwald Wheeler, among others, all physical processes are modeled according to the following paradigm. One begins with a non-interacting multiparticle state in the distant past. Non-interacting does not mean that all of the forces have been turned off, in which case, for example, protons will fall apart, but rather that there exists an interaction-free Hamiltonian H naught for which the bound states have the same energy level spectrum as the actual Hamiltonian. Hamiltonian. This initial state is referred to as the in state. Intuitively, it consists of elementary particles or bound states that are sufficiently well separated that their interaction with each other are ignored. The idea is that whatever physical process one is trying to study may be modeled as scattering process of these well separated bound states. This process is described by the full Hamiltonian, but once it's over, all of the new elementary particles and then a new bound states separate again, and one finds a new non-interacting state called the out state. The S matrix is more symmetric under relativity than the Hamiltonian because it does not require a choice of time slices to define. This paradigm allows one to calculate the probabilities of all the processes that we have observed in 70 years of particle collider experiments with remarkable accuracy. But many interesting physical phenomena do not obviously fit into this paradigm. For example, if one wishes to consider the dynamics inside of a neutron star, sometimes one wants to know more than what it is finally than what it will finally decay into. In other words, one may be interested in measurements that are not in the asymptotic future. Sometimes an asymptotic past or future is not even available. For example, it is very possible that there is no past before the Big Bang. In 1960s, the S-matrix paradigm was elevated by many physicists to a fundamental law of nature. In S-matrix theory, it was stated that any quantity that one could measure should be found in the S-matrix for some process. This idea was inspired by the physical interpretation that S-matrix techniques could give to film and diagram restricted to the Marshall and led to the construction of dual resonance models. But it was very controversial because it denied the validity of quantum field theory based on local fields and Hamiltonians. Intuitively, the slightly deformed eigenfunctions of the full Hamiltonian and in and out states, the phi, are non-interacting states that resemble the in and out states in the infinite past and infinite future. This intuitive picture is not quite right because psi is an eigenfunction of the Hamiltonian. Psi raised to plus or minus is an eigenfunction of the Hamiltonian, and so at different times only differs by a phase. Thus, in particular, the physical state does not evolve, and so it cannot become non-interacting. This problem is easily circumvented by assembling psi raised to plus or minus and phi into wave packets with some distribution Ge of energies E over characteristic scale delta E. The uncertainty principle now allows the interactions of the asymptotic states to occur over a time scale reduce Planck constant on delta E. And in particular, it is no longer inconceivable that the interactions may turn off outside this interval. The following argument suggests that this is indeed the case. Plug the Lippmann-String equation into the definitions. Psi g raised to plus or minus t is equivalent to integral of dE ei e negative I et ge psi raised to plus or minus and psi gt is equivalent to integral dE e raised to negative I e t g e phi of the wave packets. We see that at a given time, the difference between psi gt and phi gt wave packets is given by an integral over the energy E. This integral may be evaluated by defining the wave function over the complex E plane and closing the E contour using a semicircle on which the wave functions vanish. The integral over the closed contour may be evaluated using the Cauchy integral theorem as such of the residues at various poles. We will now argue that the residues of psi raised to plus or minus approach those of phi at time t approaching positive or negative infinity, and so the corresponding wave packets are equal at temporal infinity. In fact, for very positive terms t and e raised to negative iet factor in a Schrodinger picture state forces one to close the contour on the lower half plane. The pole in the phi psi from the Lipman-Schwinger equation reflects the time uncertainty of the interaction, while that in the wave packets wave functions weight functions reflect the duration of the interaction. Both of these varieties of poles occur at finite imaginary energies and so are suppressed at very large terms. The pole in the energy difference in the denominator is on the upper half plane in the case of psi, and so does not lie inside the integral contour and does not contribute to the psi integral. The remainder is equal to the phi wave packet. Thus, at very late terms, psi will be equivalent to phi, and identifying psi as the asymptotic non-interacting out state. Similarly, one may integrate the wave packet corresponding to the psi, this one raised to a positive, this term, at very negative terms. In this case, the contour needs to be closed over the upper half plane, which therefore measures the energy pole of psi, which is the lower half plane. One then finds that the psi and the phi wave packets are equal in asymptotic past, identifying psi as the asymptotic non-interacting in state. This identification of the psi's as asymptotic states is the justification of the plus or minus epsilon in the denominator of the Lippmann-Schwinger equations. The S matrix is defined to be the inner product. SAB is equivalent to psi raised to negative A plus psi raised to positive B of the earth and bith of the earth and bith Heisenberg picture asymptotic states. One may obtain a formula relating the S matrix to the potential V using the above contour integral strategy, but this time switching the roles of positive psi and negative psi. As a result, the contour now pick up the energy pole. This can be related to the phi's if one uses the S matrix to swap the two sides. Identifying the coefficients of the size on both sides of the equation, one finds the desired formula relating to the S potential. In the Born approximation, the corresponding to the first order perturbation theory, one replaces this last psi with the corresponding eigenfunction phi of the free Hamiltonian, yielding SAB is equivalent to sigma A minus B minus 2I pi sigma EA minus EB phi A V phi B, which expresses the S matrix entirely in terms of V and free Hamiltonian eigenfunctions. These formulas may in turn be used to calculate the reaction rate of the process B as it approaches A, which is equal to SAB minus sigma AB squared. With the use of the Green's function, the Lippmann-Schwinger equation has counterparts in homogenization theory, like mechanics, conductivity, and permittivity. Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself. And I will see you in the next episode of Cisco Educationals.